Hello, welcome back to our Gen Chem series, and today we're in our fifth video, and we're going to look at electronegativity and intramolecular bonding. So, as I'm sure you remember from the last video, I left you on a bit of a cliffhanger and gave you two questions to think about. So let's go ahead and start by taking a look at those. So the first question was, what did groups 3 and 5A want to do with their electrons? And also, what is strange about group 4A? So just remember, we look at group, let's start with 5A. So 5A would be this one right here, starting with nitrogen. And it's right to the left of the chalcogen group. And remember, we looked at these kind of 5 groups that I still have labeled as being really the important ones for classes in the MCAT. And we also talked about how the halogens and chalcogens want to gain some electrons to reach their noble gas configuration. And that makes sense because a halogen is just one electron away, right? The halogen, fluorine, if it had one more electron, would become the electron configuration of neon. So if we look at group 5A, then it's going to want to gain 1, 2, 3 electrons to become neon. Whereas if we look at group 3A, starting with boron, boron could gain 5 electrons to become neon, but actually it would be much easier for it to lose 1, 2, 3 of its electrons to become helium. So in that way, it can go back to a noble gas electron configuration. Finally, for group 4, what you'll notice about it is it's 4 electrons either way. It could either gain or lose 4. And that's really what makes group 4 so kind of unique. It's the only group that can both gain and lose. And so we'll see that that kind of has some interesting consequences for bonding. All right, and then the next question was, do any of the groups seem like ideal matches for each other? And maybe that question's a little oddly worded, but what I was kind of going for with this was the fact that if you think about what a halogen wants, which is to gain exactly 1 electron, and you think about what the alkali metal wants, which is to lose exactly 1 electron, they seem like a perfect match, right? They're both doing what the other one wants. So I went ahead and drew that here. So on the left, we have lithium, and on the right, we have fluorine. They're the first member of each of those groups. And so fluorine, being the first halogen, has almost a complete outer valence shell, right? So it is missing 1 spot right here. It needs 1 more electron. And I'm going to introduce an important term here. So another way to say this is fluorine needs 1 more electron to complete its octet. So octet equals the 8. So it's octet for 8. The 8 electrons needed to fill the second and third valence shells. This is especially true for the second valence shell. So all of these elements, right? All of these elements have the second shell as their valence shell, and that second shell fits up to 8 electrons. So when I say the term octet, or like completing its octet, that means filling up all 8 of the electrons and completing the shell. That's a really important and very common term that will definitely be used a lot more in some upper level classes too. Okay, so fluorine is missing 1 electron to complete its octet. Lithium is missing 7 to complete its octet, so it's not going to gain 7, but what it could do is give up its only valence electron here. Whoops. Its only valence electron. And if it gave it up and gave it to fluorine, fluorine now has its complete octet, and lithium now has a completely empty outer valence shell, meaning that it only has a completed inner shell. So it only has completed shells now. So they're both in noble gas configurations. So yeah, they're a perfect match. And the other thing I want to point out is these atoms are now charged, right? So remember that since fluorine has 9 protons by definition, that's like 9 positive charges, and when it's neutral, would have 9 electrons. But since we just gave it a 10th electron, that means it's going to have a net negative charge overall. In the lithium, the reverse is true since it lost an electron, and it's going to have a net positive charge overall, meaning that both of these atoms, both of these atoms are now ions. They're ions, which means that they're charged. Specifically, lithium is a cation and fluorine is an anion. And what we basically kind of rediscovered here in this kind of thought exercise is ionic bonding. So what we've done is we've made a bond between ions. So this is ionic bonding. And as we'll see, there's really only two kinds of bonding. The other type is called covalent. So yeah, this is our introduction for bonding. And so an ionic bond, the way to kind of think about it is the cation, and it's like a pair, and the cation is giving away its electron kind of basically permanently to the anion. Hopefully that's feeling pretty good. So I gave another example here. So you don't necessarily have to have it be that you have a pair, right? So before we looked at a halogen and paired it with an alkali metal, but we could also pair halogens with alkali earth metals. So remember, alkali earth metals want to give up 2 electrons. So if we want to pair it with a halogen, which wants to gain 1, we would need 2 halogens, right? So we can see that in the picture here. So beryllium has its 2 valence electrons. And then fluorine here, there's 2 fluorines and they both want an electron. So we're just simply going to, again, steal our electrons from the beryllium, move it on over, and complete everybody's octet, or really complete the fluorine's octet, and now the beryllium just has an inner shell that's full. And so everybody's happy. And this is also ionic bonding, and in this case, the beryllium would be a +2. It would have a 2 plus charge. Actually, sorry, I kind of write that like this. And the fluorines would both be negative. Yep, so this is another good example of ionic bonding. Now let's talk about the other form of bonding that I already mentioned, which is covalent bonding. So the main difference is that in covalent bonding, the electrons are shared. So comparing that to an ionic bond, right, we saw that the electrons are kind of permanently given up. So the cations give up their electrons forever to the anions. Whereas in covalent bonding, the atoms are going to share their electrons in order to fill their orbitals. Or I guess in this case, shells. So let's look at an example of this, because I think seeing an example makes it a little more clear what I mean by share. So let's look at everybody's kind of favorite molecule, which is water. So we've got an oxygen in the middle, 2 hydrogens on the sides. We've got our H2O. And let's kind of think about what they need again. So the oxygen has 2 empty spots. It needs to fill here and here to complete its octet. And then the hydrogens also have an empty spot, right? So they want 1 more electron as well. And hydrogens, since they're kind of special and only have like literally 1 shell because they're so small, this is called their duet. An octet, right? Because it's not 8 electrons, it's just 2 to fill the shell. So it's called a duet, which I honestly think is really cute. So a hydrogen is looking for 1 electron and the oxygen is looking for 2. So if we combine the 2 hydrogens, we can kind of put them together like this. And you can see that they just kind of perfectly fit. And with this arrangement, all of the valence shells are now complete. We've completed the duets of the hydrogen and the octets of the oxygen, which is kind of amazing. And this area where the electrons are being shared, that is kind of what we think of when we say the word bond. So usually when people are saying the word bond in high school, college, really just any time, this is really what people mean. This is what kind of the prototypical bond is the area where the shared electrons live. So I want to cover one more thing with this video, which is the concept of polarity. And before I define that, I want to talk a little bit more about what it means to share an electron. I feel like it's a little bit kind of nebulous. It's like, what does the word share actually mean in this context? How's an electron actually shared? So to start by answering that, I want us to remember kind of what's physically going on, right, with electrons. So if we're kind of using this electron in green right here as our example bonding electron, if I say that it's shared, what that means is the electron is spending its time split between both atoms in a bond. And the reason that makes sense is bonds are similar to orbitals. So electron orbitals, right? Remember that the electrons are constantly moving in their orbital. Like a p orbital, yeah, they're constantly moving in that dumbbell shape, and they can exist kind of anywhere in that dumbbell. And for a bond, it's kind of a lot more complicated, but the kind of idea is the same, which is that the electrons are kind of orbiting both electrons now in this like new bond orbital. And roughly speaking, you can kind of think of it as being like this kind of shape. And there's a kind of a couple phrases for this, which is like electron cloud or density. And it's just referring to the fact that anywhere in this area, actually, maybe that is a little bit too big, but really anywhere in this area, the electron could be. It could be kind of near the hydrogen or near the oxygen, and it's constantly moving and bouncing around between those locations. And so polarity is all about how the electrons are shared. It's a really important concept. So as it turns out, um, molecules oftentimes aren't like perfectly sharing their electrons. In fact, water's a really, really good example of this. And so when electrons are not perfectly shared, it's called a polar molecule, or the molecule is polarized, or it's a polar bond. Lots of phrases for that. And what that means, yeah, is the electron is spending more of its time at one of the atoms than the other. So it's an unequal sharing. So I want you to spend a moment and kind of think about what your guess would be as to which atom in the water molecule the electrons will spend more time at. Do you think it's going to be the hydrogens or the oxygen? And just to give you a little hint to kind of get you started, um, the explanation is going to kind of require you to incorporate the periodic trends that we talked about in the previous video. Okay, hopefully you spent a little bit of time thinking about that. And it's going to come back to the mother of all the trends, our effective nuclear charge. So effective nuclear charge is more or less the reason. So not going to go over how I calculate these because you can see that in the previous videos, but the Z effective of oxygen is 6 and hydrogen is 1. So let's kind of remind ourselves conceptually what that means. So this is saying that the effective nuclear charge of oxygen is higher, which means that it's like proton pulling force, how hard it's pulling on the electrons is increasing. So if we're looking at our green valence electron, it's getting sucked into the oxygen atom with more force than kind of the measly hydrogen. So the hydrogen atom's kind of weak. It has like a proton force of like this one little arrow that I drew, and oxygen's got 6. So it's really pulling on the electrons in the bond, which means that the bond, the density of the bond is actually going to be really lopsided towards the oxygen. The electrons are going to spend most of their time around the oxygen, and we call that a polar bond. And there's another kind of important concept here. So remember what happened in an ionic bond, right? We kind of permanently gave away an electron from one atom to another. So that's like a super unequal sharing, right? You like permanently gave it away to the other one. Um, so in ionic bonds, it's so unequal that you end up with permanent charges, right? Remember the fluorine became negative because it gained an electron basically permanently, and the beryllium became positive because it gave away electrons basically permanently. So now the fluorine has an extra electron compared to the amount of protons it used to have, and the beryllium's got extra protons compared to the electrons. So there's charges now. And the same thing is going to happen with our polar molecules too, just to like a slightly less extent, right? So I'm going to erase some of this stuff to make some room. But one of the ideas here is that now the oxygen, since it's getting the bigger share of the electron density, is going to have a partial negative charge. So in chemistry, the partial negative charge is denoted with this kind of like almost figure eight symbol. And the partial positive charge is going to go to the hydrogens, right? So they're going to be partially positive because they lost some electrons most of the time. And so if you kind of draw that out, it's like the oxygen is going to be like a cloud of negative charge, like partial negative charge, and the hydrogens are like little regions of partial positive charges. And this ends up being really, really important for kind of the properties of water. And we'll talk about this a lot more when we talk about intermolecular forces. Polarity really kind of explains so much. So kind of to sum this up in another way, you can really think of bonding as being more of a spectrum. It's not really so much that there's these two different ways to bond, covalent and ionic, really that there is a spectrum of ways to bond. And you can fall anywhere on this spectrum. With the one extreme on the far right being an ionic, where you completely give an electron away forever to one of the atoms, and the other being a nonpolar covalent bond, where the sharing is completely equal. And notice that the example they give is Cl2. So it's two chlorines that are bonded to each other. So it makes sense that that would be nonpolar, because if they're both the same element, they're going to share their electrons equally. Not only do they have the same effective nuclear charge, but they're literally the same. There's no difference. So the electrons are just going to orbit equally. Okay, so one of the kind of follow-up questions to this is like, well, what's really the cutoff then? How do I know if something is considered ionic versus polar covalent? At what point do we kind of consider it something to be one type of bond over the other if it's a spectrum? And at the end of the day, it is kind of arbitrary. It's really like human definition. But we do have a pretty good consensus as to what makes something ionic versus polar covalent. And it all comes down to my favorite periodic trend, the most important periodic trend, electronegativity. So I like to say that, and stay with me here, I know this is a bit of a tangent, but I like to say that electronegativity is this is a measure for how selfish is an element with electrons. So looking at our kind of periodic table of selfishness right here, we can see that fluorine is the most selfish element with its electrons. And the elements kind of on the left in this region aren't particularly, like, they're very unselfish. They're very willing to share. And so what this is trying to say really is it's trying to say fluorine wants an electron really bad, which kind of makes sense from where we started the video, right? We saw that fluorine desperately wants to gain one electron, right, to become a noble gas. So it makes sense that it would be a really selfish element. It really wants to hold on to electrons, kind of similar with oxygen. And then it makes sense for lithium and beryllium and the other elements in the same group to be very willing to share, because they actually just want to give up an electron permanently so they can also become a noble gas configuration. And so the way we actually end up defining what the different bonds are is by using the differences in electronegativity. So for example, we looked at lithium fluoride earlier today. So, and we learned that it was an ionic bond. And if you see the difference in electronegativity, you have about 4 for fluorine, and then lithium is about 1. So 4 minus 1 is 3. So they have a difference in electronegativity of about 3. And generally speaking, the cutoff for ionic bond is about 1.7. So anything greater than a difference of 1.7 is considered ionic. So since LIF is a difference of 3, it's as ionic as it can possibly be, basically. It's extremely unequal sharing of electrons. So put kind of 3 at the extreme here. And then another example would be something like hydrocarbons. So carbon has an electronegativity of 2.55, and hydrogen has 2.20. And hydrocarbons are a really important molecule in life and in organic chemistry. And a hydrocarbon is just a molecule made of nothing but carbon and hydrogen. And since their electronegativity difference is only 0.35, so kind of all the way down here near zero. So I'm just going to write like methane, for example. It's a hydrocarbon. It's considered nonpolar, so it's essentially just an equal sharing of electrons. And the cutoff for nonpolar is typically about 0 0.5. So that means in this 0 0.5 to 1.7 region is the polar covalent. And yeah, we can double check that water is polar covalent. So water is oxygen and hydrogen. Oxygen's 3.44, hydrogen's 2.2. So that's a difference of about 1.2. So yeah, water is like squarely in the middle here and would thus be a polar covalent bond. Okay, I hope we're feeling pretty good about bonding. There's still quite a bit more to talk about. And normally I would kind of like to end this video on a question, but actually I want to kind of tell you about the next video I'm going to be making kind of ahead of time, because the next video I'm going to do a little differently. So I want to, like, every 5 videos or so, kind of make a special kind of quiz video. So what I'm going to do is in the description of my next video is going to be like a PDF of a worksheet, or kind of like a quiz, and it's going to be covering all of the content that we've talked about so far. And so in my next video, it's just going to be me going over that worksheet. So you could just open up the description, download it, give it a try before watching. And then, yeah, we can go over it together. You can kind of treat it like a little review midterm or review quiz, but with no stress. Um, so I really hope that's helpful. I hope that's something that you'd be interested in. And thanks for watching.